Hi, I am Sushma, working as Assistant Professor in the Department of ECE in Institute of Aeronautical Engineering College. In this session, we are going to discuss about the multiplexer and demultiplexer. So, what is multiplexer and what is demultiplexer? In network transmission, both the multiplexer and demultiplexer are combinational circuit. Here, both multiplexers and demultiplexers are combinational circuit. What is combinational circuit? Combinational circuit, the output depends on the only present values of the input values. So here both multiplexer and demultiplexers are the combinational circuit. A multiplexer selects an input from several inputs. Okay, it has many inputs and one output. According to the selection lines, it will select the any one of the input to the output. So this multiplexer is also called as a data selector or many to one selector also. Okay. A demultiplexer uses one input signal and generates many. So it is known as demux or data distributor. So the difference between the multiplexer and demultiplexer is multiplexer has many inputs and one output, whereas demultiplexer has the one input and many outputs. So if we see this figure of multiplexer and demultiplexer, in this multiplexer we have inputs, many inputs and only one output. Okay, according to these selection lines, or we can call these are control signals. Okay, according to these selection lines, any one of the input will be transmitted to the output. Okay, that is known as multiplexer. Whereas in demultiplexer, it will take one input and according to the selection line, it will route to the any one of the outputs. Okay, this is demultiplexer. So, we will discuss what is multiplexer and designing of 2x1 multiplexer, 4x1 multiplexer, 8x1 multiplexer and 16x1 multiplexer first. Okay, it is what is multiplexer? It is a combinational circuit which have many data inputs and single output. Okay, depending on the control or selection lines, any one of the input will be transmitted to the output. So here, if we consider the multiplexer, it denotes the 2 to the power of n inputs and 1 output. Okay, this n denotes the selection lines. Okay, n number of selection lines. So here, suppose if we have 2 by 1 mux means 2 power 1 into 1. So this multiplexer, 2 by 1 multiplexer has 2 inputs, I0 and I1, and this n is here 1. So 1 selection line, that may be S0, and 1 output, Y. Okay, 2 by 1 mux. For example, if we are taking 4 by 1 mux, 4 by 1 mux, 4 indicates here 4 inputs, I0, I1, I2, I3. So 4 we can write this as a 2 power 2 into 1. In terms of 2 power, we have to write that one. So this 2 indicates selection lines. 2 selection lines we have S0 and S1 and 1 output Y. Okay. So for example, if we have 8 by 1 mux, 8 by 1 mux is 2 power 3 into 1. So 2 power 3 means 3 selection lines, total 2 power 3 inputs and 1 output. Okay. This is the basic multiplexer block diagram. So here for n input lines, log n selection lines we have, or we can say that for 2 power n input lines, n indicates the selection lines. Multiplexer also known as data selector or parallel to serial converter and many to one circuit are universal logic circuits. In so many applications, we will use the multiplexer to transmit the one input to the output from many inputs. Multiplexers are mainly used to increase the amount of data that can be sent over the network within certain amount of time and bandwidth. So first we will discuss 2x1 multiplexer. Okay, in 2x1 multiplexer, the multiplexer symbol, first we will discuss the symbol here. This is the symbol of multiplexer. Okay, so inputs we are giving is 2 power n inputs we are giving, n selection lines, and for any multiplexer only we have one output. So this is the symbol of multiplexer. Okay, so if we consider the 2x1 multiplexer, so it has 2 inputs. If you observe this block diagram, we have 2 inputs, 1 output, 2 power 1. So this 1 indicates the selection line. So for 2x1 multiplexer, we have only one selection line. According to this selection line, it will map the input to the output, any one of the input to the output. So here, if we observe this truth table, here input, we are according to the selection line, it shows them whatever the input either it may be 0 or 1, that will be mapped to the output. So here, if S0 is 0 for 2x1 mux, this selection line whatever we are taking, 2x1 multiplexer, we have only one selection line, we are considering that as S0. Okay, if S0 is 0, then A0 will be mapped to your output. Okay, A0 signal will be transmitted to the output. That is whether A0 0, you will get the output 0. If A0 is 1, you will get output 1. Okay, so whatever the data present in A0, that will transmitted to the output if S0 is 0. Okay, if S0 is 1, A1 data will be transmitted to the output. So whether it may be 0 or 1, whatever the data present in the A1, that will be transmitted to the output. So according to the selection line, if it is 0, we are getting A0. If it is 1, we are getting A1. So this is the functioning of the 2x1 multiplexer. So the symbol for 2x1 multiplexer is, so we have 2 inputs, okay, A0 and A1, one selection line, that is S0, and one output Y. So this is 2x1 mux symbol. Okay. If we draw the logic diagram of the 2x1 multiplexer, so in this truth table, if we write the output equation, we can write Y0 is equal A0, S0 is 0. We can write that as A0, S0 bar plus A1, S1, S0. Okay. So this is the equation for the 2x1 mux output. So we have to realize this equation into logic diagram. So here we got the equation as Y is equal A0, S0 bar plus A1, S0. Okay. So here this S0 is we are taking as selection line. So first A0, S0. So this is one product and A1, S0 also one product. For A0, S0 for multiplication we are using AND gate. So here we are getting A0, and to get S0 bar we are giving S0 to the inverter. So here we are going to get S0 bar. Okay. If we give the A0 and S0 bar to the AND gate, here the product we will going to get the A0, S0 bar. And for second AND gate, okay, one of the input is A1, another input is S0. So the product, the output of the AND gate is A1, S0. So we are giving these two products to the OR gate. So here we are going to get A0, S0 bar plus A1, S0 bar. So we are adding these two product terms here by using OR gate. So A0, S0 bar plus A1, S0 bar. This is the logic diagram of the 2x1 multiplexer. So 4x1 multiplexer. So how to design 4x1 multiplexer? We know 4x1 multiplexer into 4 inputs, 1 output. So we can write 4x1 in terms of 2 powers, 2 power n in cross 1. So This 2 indicates the selection lines. So, if this total 2 power 2 is inputs and 1 output. Okay. So, here 2 power 2 total we have 4 inputs, 1 output and 2 power 2. The 2 power 2 is the selection line. So, we have 2 selection line here, S0 and S1. Okay. So, according to the selection line values, we will any one of the input will be transmitted to the output. Okay. If S0 and S0 is 0, 0, then I0 will be transmitted to the I0, whatever the data is the I0, that will be transmitted to the Y. If S1 and S0 is 0, 1, I1 will be transmitted to the Y. If 1, 0, I2 will be transmitted, 1, 1, I3 will be transmitted. Other data will not be transmitted to the output. Only according to the selection lines, any one of the input will be transmitted to the output. So, if we observe the truth table of the 4x1 mux, here according to the selection line values, we will get the output. Okay. If we have 2 selection lines, then we will get the 4 combinations 0, 0, 0, 1, 1, 0, 1, 1. If S1 and S0 both are 0, then by whatever the data present here the I0, that will be transmitted to the output. Okay, and remaining inputs will be disabled. Only I0 will be enabled and that will be transmitted to the output. And when S1 is 0 and S0 is 1, then I1 will be transmitted to the output. If S1, S0 1, 0, then whatever the data at the I2, that will be transmitted at the output. If 1, 1, then it will be I3 will be transmitted at the output. Okay. If we write the equation by using truth table, so if we first term is this one, okay, and that is nothing but this we can write as 0 means this is S1 bar and S0 bar, I0. So S1 bar, S0 bar, I0. The first one term is S1 bar, S0 bar and I0. And second term is this is S1 bar and this is S0 and I1. S1 bar into S0 into I1. This is the second product term. And third product term, this is S1, 1. If it is 1, we can write that as S1. If it is 0, we have to write that is S1 bar. If it is 0, S0 bar, 1, S0. That's all, S0. Okay. So, in third product term, we can write S1, S0 bar, I2. S1, S0 bar, I2. In third product term, we can write this is S1 into S0 into I3. S1 into S0 into I3. So we have to sum these product terms. So we will get the equation y is equal to S1 bar S0 bar I0 plus S1 bar S0 I1 plus S1 S0 bar I2 plus S1 S0 I3. So this is the equation, output equation for the 4x1 multiplexer. We have to realize the, we have to draw the logic diagram by using this equation. Okay. So if we see this equation, we will get y is equal to S1 bar S0 bar I0 plus S1 bar S0 I1 plus S1 S0 bar I2 plus S1 S0 I3. So this is the logical, this is the output equation of the 4x1 multiplexer. So here if we see, if we observe the logic diagram, so we will draw the first product term. Okay. So to get the S1 bar and S0 bar, we have to give the S1 and S0 selection lines to the inverter, not get. Then we will get the, so here we are taking two selection lines S1 and S0, and if we give the S1 to the inverter, here we are going to get S1 bar, and if we give the S0 to the inverter, we are going to get the S0 bar. Okay. So in first product term, this S1 and S0 I3, this we are giving I3. So directly we are giving S1, S0 and this is I3 to the AND gate. The output of this AND gate is we are going to get S1, S0, I3. And second, this product term S1, S0 bar, I2. So here we are getting S1 directly, we are giving S1 here, and the S1 we are giving, S0 we are giving to the inverter, we are going to get that as S0 bar. So that output of the inverter is given to the AND gate S0 bar and I2. So these three will be multiplied if we give the AND gate. So this term is I2. Okay. And third gate, this product term S1 dash, S0 and I1. So here one input to the AND gate is S1 bar and this we are giving from here, that is S0 and I1. So the product term we are going to S1 bar, S0, I1. Okay. And for last gate S1 dash, S0 dash, I2. So here this is S1 dash and this is S0 dash and I2. So here the product term S1 dash, S0 dash and I0. Okay. So we are adding all this product. So for plus we have to use the OR gate, OR operation. So here we are giving all these product terms to the OR gate. Okay. So these all are the inputs to the OR gate. Here we are going to get the output of Y as this one. Okay. Summation of all these product terms. This is the 4x1 multiplexer logic diagram. So 8x1 multiplexer. So already we know for 8x1 multiplexer we have the symbol for the 8x1 multiplexer is, so only we will get the one output and we have the inputs from A7 to A0, totally 8 outputs. So this is, we can write 2 power 3 into 1. So 2 power 3, this 3 indicates the 3 selection lines. We have 3 selection lines here, S1, S2, S1, S0, S2, S1, S0. And one output, total 2 power 3 inputs, that is 8 inputs. So this is a block diagram of the 8x1 multiplexer. Total A0 to A7, 8 inputs we have. So 2 power 3 by 1 we can write this one. So this 3 indicates the 3 selection line, S2, S1, S0 and 1 output. Okay. So here how to draw the logic diagram of the 8x1 multiplexer. So first we have to know the truth table of 8x1 multiplexer, how to write the truth table for the 8x1 multiplexer. So here we have 3 selection lines, S2, S1, S0. Okay. For 3 selection lines we have 8 combinations, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. So according to the selection line, any one of the input will be transmitted to the output. So for if we give the selection line's input is 0, 0, 0, then output A0 will be transmitted to the output. Whatever the data present in the A0, that will be transmitted to the output. If it is 0, 0, 1, A1 will be transmitted, 0, 1, 0, A2, 0, 1, 1, A3, 1, 0, 0, A4, 1, 0, 1, A5, 1, 1, 0, A6, 1, 1, 1, A7. Okay. From the truth table, we have to write the logical expression of the output. By using this, we have to write the draw the logic diagram. Okay. So if we observe the expression of the output of the 8x1 multiplexer, first product term is here S2 bar, S1 bar, S0 bar into A0. So this is the first product term, S0 bar, S1 bar, S2 bar into A0. And second product term, this is S2 bar, this is S1 bar, this is, if we have 1, we have to write S0, if it is 0, we have to write S0 bar. So S2 bar, S1 bar S0 into A1. So this is the second product term. So see here S0, S1 bar, S2 bar, A1. So this is the second product term. Okay. For third product term, this is S2 bar, S1, S0 bar into A2. S2 bar, S1, S2 bar into A2. Third product term, this we can write as S3 bar, S1 into S2, A3. And fourth product term, this is third one for A3. Fourth one is S1 and S2 and S1 bar and S0 bar. S2, S1 bar and S0 bar into A4. For A5, the product term is S2, S1 bar and S0 into A5. So this one. And this product term S2 into S1 into S0 bar is into A6. And last product term is S1, S2 into S1 into S0 into A7. So we have to write all these product terms and we have to add all these product terms. We will get the logical expression of the output. So here if you observe, we have the three selection lines and we have the S0 bar and S1 bar and S2 bar also in product terms. So to get that one, we have to give that input to the inverters. Then we will get the S2 bar, S1 bar and S0 bar. Okay. So first we have to write the three selection lines and another lines for the complement of that selection lines. So S2 bar to get S1 bar and S0 bar, we are using these inverters. Okay. So here G1, G0, G1, G2, G3, G4, G5, G6 and G7. If we for first get G0, so the first product term is S0 bar, S1 bar, S2 bar, A0. So here we are giving connecting. So connecting for first product term for A0. So we have to connect the S0, A0 into S1 bar and S2 bar into S0 bar into A0. So like that each product term we are giving to the AND gates and we are adding these product terms. So that's why we are using here OR gate. So these all product terms output, the AND gate outputs will be ORed and then we are going to get the output Y. So this is the logic diagram of the 8x1 multiplexer. So here implementation of higher order multiplexer. So here if we go further 16x1 multiplexer or 30x1 multiplexer, by using this 8x1 multiplexer or 4x1 multiplexer, we how to realize the higher order multiplexer we have to discuss. We are going to discuss now. Okay. So here let us implement the following two higher order multiplexer using lower order multiplexers. That is 8x1 multiplexer and 16x1 multiplexer. So in 8x1 multiplexer, by using 4x1 multiplexer and 2x1 multiplexer, we have to implement. Okay. So for that, 4x1 multiplexer has 4 input lines and 2 selection lines and 1 output. Whereas 8x1 multiplexer, it has 8 inputs and 3 selection lines and 1 output. Okay. So here we have to realize the 8x1 multiplexer using 4x1 mux and 2x1 mux. So we have to design 8x1 multiplexer using 4x1 multiplexer and 2x1 multiplexer. So here for that design we have 2 4x1 multiplexers and 1 2x1 multiplexer to design the 8x1 multiplexer. So here we know the truth table of the 8x1 multiplexer. Already we discussed this one. Okay. Here for 8x1 multiplexer we have 3 selection lines S2, S1 and S0. According to the selection line we will get the output. Okay. Any one of the input will be transmitted to the output. So how to draw the 8 by 1 multiplexer using 4 by 1 mux. Okay, here we are going to use two 4 by 1 multiplexers and two 1 by 1 or 2 by 1 multiplexer is one. We are going to use that one. If you observe this truth table, okay, so leave S2, only observe S0 and S1. See, these two values will be same, repeating. Okay, 0 0 0 0 0 1 0 1 1 0 1 0 1 1 1 1. Okay, so these S1 and S0, for these two groups both are repeating. Okay, so that's why here these S1 and S0 we are giving to the both 4 by 1 multiplexers. Okay, so here if S1 and S0 we are giving selection lines to the both multiplexers, and inputs for the one is from I0 to I3, and for another multiplexer I4 to I7. So here we are getting two outputs, one from the 4 by 1 multiplexer and another from the another 4 by 1 multiplexer. Okay, but for 8 by 1 multiplexer we have 8 inputs and 1 output. Okay, any one of the output should be mapped to the output. So to select from these two, any one to the one input to the mapped to the output. So here we are using 2 by 1 multiplexer. Another selection line, this S2. If S2 is 0, these lines from I0 to I3 will be any one will be mapped. If S2 is equal 1, then I4 to I7 will be, any one will be mapped to the output. Okay, so here for S2 we are giving to the 2 by 1 multiplexer as a selection line, and the outputs of the 4 by 1 multiplexer is given to the input to the 2 by 1 multiplexer here. Okay, for example we are taking S0, S1 and S2 1 0 1. Okay, so here S0 is 0, S1 is 1. Okay, so in this multiplexer for 0, if it is 0 0, then I4 will be mapped. If it is 0 1, I5 will be mapped. If it is 1 0, I6 will be mapped. Okay, if it is 1 1, I7 will be mapped. Okay, so here if it is 1 0, then I6 will come here. Okay, then here if it is 1 0, for 0 0 selection line it will we are going to get the I0 0 1 1 0 1 1. Okay, so for 1 0 we are getting here I2. Okay, I6 and I2 are the outputs of the multiplexer, 4 by 1 multiplexer. These are given to the input to the 2 by 1 multiplexer. Okay, here S2 is 1. If S2 is 0, I2 will be mapped. If S2 is 1, I6 will be mapped here. Okay, so here we are going to get here I6. So if you observe truth table for here for 8 by 1 multiplexer, we by using 4 by 1 multiplexer we have to implement 8 by 1 multiplexer here. For that we are using two 4 by 1 multiplexers and one 2 by 1 multiplexer. Okay, here for this one, for example I am taking S2, S1, S0 is 1 1 0. Okay, so S1 is 1, S0 is 0 here. Okay, so S1 is 1, S0 is 0. For here for 0 0 1 0 we are going to map this I6 here. Okay, 0 0 I4 will be mapped, 0 1 selection line I6 I5 will be transmitted, and 1 0 I6 will be transmitted. For selection line 1 1 I7 will be transmitted. Okay, for selection lines. Okay, S1 and S0. Okay, so for 1 0 I6 will be mapped to the output of this first 4 by 1 multiplexer, and for 1 0 here So for 0, 0, for selection line 0, 0, I0 will be mapped 0, 1, I1 will be mapped 1, 0, I2, 1, 1, I3. So here for 1, 0, we are giving S1 and S0 as 1, 0. So I2 data will be transmitted to the output of this transmission multiplexer. Okay. So here I6 and I2 are the outputs of the multiplexer. Here these are the inputs to this second multiplexer. Okay. So the second multiplexer S2 is 1. So here we are giving 1 here. Okay. So if it is 0, selection line is 0, I2 will be transmitted in the output. If it is 1, I6 will be transmitted to the output. So here we are giving S2 is 1, then I6 will be transmitted at the output. We are getting whatever the data presented the I6, that will be transmitting to the output Y. So see here, if you observe for 1, 1, 0, we are getting I6. So here also if we give the selection line 1, 1, 0, we are getting output I6. Okay. If we see 1, 1, 1 also, so for 1, 1 here, this second, this first multiplexer and this is the second multiplexer. The second multiplexer output will be I3 and first multiplexer will be I7 for 1, 1 if it is 1 and 1. Okay. And then if it is the 1, 1 selection line, here we are getting I7 and I3. If the selection line for the S2 is 1, so I7, if it is 0, I3 will be mapped for this 2 by 1 multiplexer. 1 means I7 will be mapped. So if it is 1 means I7 will be coming to the output. So that's why here we are getting output I7. So like that we have to realize the 8 by 1 multiplexer using 4 by 1 multiplexers. So the same selection lines S1 and S0 are applied to the both 4 by 1 multiplexers, and the data inputs upper 4 by 1 multiplexers are I7 to I4 and the lower multiplexers are I3 to I0. Okay. The output of these two 4 by 1 multiplexers are given to the 2 by 1 multiplexers, and these 2 by 1 multiplexer has a selection line is S2 and the inputs are from the outputs of the 4 by 1 multiplexer and it has only one output. So this is the realization of 8 by 1 multiplexer using 4 by 1 mux and 2 by 1 mux. So if we draw the 16 by 1 multiplexer, here we have to implement 16 by 1 multiplexer using 8 by 1 mux and 2 by 1 mux. So here for 8 by 1 mux and 2 by 1 mux, here we have to use 2 8 by 1 multiplexers and 1 2 by 1 multiplexers. Okay. So here the first, this first and this is the second 8 by 1 multiplexer. For first 8 by 1 multiplexer, we are giving from I0 to I7 and second multiplexer, second of I7 to I15. Okay. For 16 by multiplexer, we have 4 selection lines. Okay. So those are S3, S2, S1, S0. So these S0, S1, S2 are the selection lines for this both 8 by 1 multiplexer. We are giving common selection lines to both multiplexer S2, S1, S0. Okay. And this S3 will be the selection line for the 2 by 1 multiplexer. Okay. So we are getting one output from the 8 by 1 multiplexer and one output from the another 8 by 1 multiplexer. According to the S3, on any one of the outputs will be transmitted to the final output Y. So this is the realization of 16 by 1 multiplexer using 8 by 1 and 2 by 1 multiplexer. If you want to draw the 4 by 1 multiplexer, here we have selection lines S3, S2, S0 not for the 4 by 1 multiplexer. So first 4. So 4 means here 4 by 1. So it has 4 inputs, but we have total 16 inputs. So that's why we have to use 4 by 1 multiplexers. Then we will get the 16 inputs. So draw 4. 4x1 multiplexers. So here from I0 to I3, each gate has 4 inputs, I4 to I5, I6, I7, I8 to I9, I10, I11, I12, I13, I14, I16, I15, 12, 13, 14, 15. So each one has the 4 inputs. So here I13, I14 and it has I10 and I9, I6 and I5 and we have I2 and I1. Okay. So first two selection lines S0 and S1 are the selection lines for the all 3 gates. So S0 and S1 draw 2 lines parallel here. So these are the selection lines for the all gates, all multiplexers. Okay, so here we are going to get one output from all multiplexer, one output. Okay, so these outputs I am taking, these are the A0, A1, A2, A3. So again these outputs are given to the 4x1 multiplexer. So here the selection lines are remaining S3 and S2. We are going to get here one output. This is the realization of 16x1 multiplexer using 4x1 multiplexer. Here totally we are using 5 4x1 multiplexers to realize the 16x1 multiplexers. So the applications of the multiplexers are, we are going to use in communication system, computer memory and telephone network, and transmission from computer system of the satellite, communication system, arithmetic logic unit, serial to parallel converter and photo credits. So demultiplexer. So demultiplexer is also a combinational circuit which is has the one input. If you observe this block diagram, it has only one input and many outputs. According to the selection lines, it will route the input to the any one of the output. Okay. So it has one input and 2 to the power of n outputs. This n indicates the selection lines. Okay. Simply the demultiplexer is a single input and multi-output combinational circuit. So here the information is received from the single input lines and directed to the output line, any one of the output line. On the basis of the values of the selection lines, whatever the selection lines inputs we are giving, according to those values, the input will be routed to the any one of the output. So here this is demultiplexer function is opposite to the multiplexer functionality. Okay. So it is also known as data distributor, whereas multiplexer is known as data selector, whereas demultiplexer is known as data distributor. So if we observe the demultiplexer, the symbol for the demultiplexer is one input and many outputs. Okay. So 2 to the power of n outputs, one input and n selection lines. So 1 by 2 to the power of n. Okay. So we have 1 by 2, 1 by 4, 1 by 8, 1 by 16. Like that we have demultiplexer designing. Here 1 by 2 demultiplexer. It has one input and 2 outputs, 2 power 1. So 1 selection line. Okay. If S0 is 0, the selection line is 0, then whatever the input that will be routed to the Y0. So whatever the Y0 is there, that will be routed to the Y0. So we are going to get Y0 is A and another output will be disabled. Okay. If A0 is 1, this input will be routed to the Y0. This output will be disabled and whatever the data at the A, there it may be 0 or 1, that will be transmitted to the Y1. Okay, if we realize that into the logic diagram, so here we can write S naught. So S naught Y. Okay, A will be given here and A will be given to the another AND gate. If S naught is 0, so that is here, this will be S naught bar A and this term is S naught A. So S naught bar, if we give the S naught to the inverter, we are getting S naught bar and A, and directly we are getting A and S naught. Okay, so if we give the S naught is 0, so for example S naught is equal 0. If S naught is equal 0, then here in the for the first AND gate we are getting the here S naught is 0 means after inversion here we are getting 1, here we are getting A. Okay, second AND gate directly we are getting here 0 and A. If any one of the input to the AND gate is 0, then output is 0. So here we are getting Y1 is 0 and whatever the here one of the input to the AND gate is 1 and another is A. So whatever the A is there, that will be transmitted to the Y0. If it is 0, 0 will be transmitted. If it is 1, 1 will be transmitted to the Y0. So here we are getting A. So this is the logic diagram of demultiplexer. To get the 1/4 demultiplexer, so here 1/4. So we can write as 1/2 power 2. So it has only one input and 4 outputs, Y0, Y1, Y2, Y3, 2 selection lines, 2 power 2. So we have 2 selection lines, S0 and S1. So we have to realize first how many inputs, how many outputs, what are the selection lines for the demultiplexer. Then if we observe the truth table, if S1 and S0 are 0, 0, then whatever the A data, the data present at the A, that will be transmitted to the Y0, routed to the Y0. Another will be disabled. So Y0 is A. Okay. If it is 0, 1, then A will be routed to the Y1. So Y1 is A, another outputs are disabled. Okay. If it is 1, 0, then A will be routed to the Y2. Y2 is A, other outputs are disabled. If it is 1, 1, then if S0 and S1 is 1, 1, Y3 will be A and other outputs are disabled. So here if we observe Y0, so Y0 we can write as S1 bar, S0 bar into A. Y2 we can write as S1 bar, S0 into A. It is S1, S0 bar into A. Y3 is S1, S0 into A. So these are the output of the demultiplexers. By using those equations, we have to realize the logic diagram. Here we are getting Y3 is equal, Y0 is equal S1 bar, S1 bar A. Here, if you see here, Y1 is S1 bar, S0 A, S0, S1 bar A, Y2. Here, S0, S1 into A. So these product terms we are using. So these S0 and S1 and A, we are giving to the inputs to the this AND gate. S0, S1 dash A inputs given to the this AND gate. S0 bar, S0 A will be given to this AND gate. To get this product term S0 dash, S1 dash and A, we are giving these lines to the this product term. Okay, so then we are going to get Y3, Y2, Y1, Y0. So for 1/8 multiplexer, so 1/8 we can write that as 1/2 power 3. 3 selection lines we have S0, S1 and S0. According to these selection line values, the A will be routed to the any one of the output. Another outputs will be disabled. So according to these selection lines, output will be selected. So we have to write these equations by using truth tables. Okay. For 0, 0, 0, Y0 will be selected. So 0 means S0, S1 dash, S2 dash. 0, 0, 1. Like that we have to write these equations and we have to realize that into logic diagram. So 0, 0, 0 means y0 will be selected, other outputs will be disabled. If 0, 0, 1 means y1 will be selected as A, other outputs will be disabled. If 0, 1, 0, the input routed to the y2, 0, 1, 1, it routed to the y3, 1, 0, 0, the input is routed to the y4, 1, 0, 1, y5, 1, 1, 0, y6, 1, 1, 1, y7. Other outputs will be disabled. According to the selection line, any one the input is routed to the any one of the output line. So this is the logic diagram of the demultiplexer. Okay. So we have to S0 dash, S1 dash, S2 dash into A. Like that we have to realize the outputs by using logic gates. So here we have 1/8 demultiplexer using 1/4 and 1/2 demultiplexer. Here for that one, to implement 1/8 demultiplexer, we are using two 1/4 multiplexers and one 1/2 demultiplexers. So we know already 1/4 demultiplexer has one input and 4 outputs and 2 selection lines, whereas 1/2 multiplexer has one input, one selection line and 2 outputs. So for getting 8 data outputs, we need to 1/4 demultiplexer, because 1/4 multiplexer has 4 outputs and another 1/4 has 4 outputs. So total 8 outputs we are getting by using two 1/4 multiplexers. Okay, but selection lines will be given common here, S0 and S1. Okay, so here by using 1/2 demultiplexer, here we are giving one input and 2 outputs for the 1/2 demultiplexer according to the selection line S2. If S2 is 0, then output will be routed to this line, and if it is 1, then it will be routed to this line. Okay, so these two lines are input to the 1/4 demultiplexer and another 1/4 demultiplexer, and we have for 1/8 we have 3 selection lines. So this S2 will be the selection line for 1/2 demultiplexer, and another S0 and S0. Now S1 and S0 are the selection line for the another 1/4 demultiplexers. Okay, here we are going to get 4 outputs from one demultiplexer, another 4 outputs from another demultiplexer. Okay, so this is the 16/1 multiplexer using 1/8 and 2/8. So here total we have to get 16 outputs. So 16 outputs means 1/8 has 8 outputs and another 1/8 has 8 outputs. Okay, to get these two inputs, we have the 1/2 multiplexer. So these two inputs to these 1/8 multiplexers are given from the 1/2 multiplexer. Here we have selection lines for these two are S1 and S0. Here we have S2. 3 selection lines we have. So S2, S1, S0. This is S3, and we have one input, that is I. Okay. So like that we have to realize the demultiplexers using 1/2 and 1/8 demultiplexer. So demultiplexer is used to connect a single source to multiple destinations. Okay. We have only one input, but this input should be mapped to the any one of the output according to the selection line. So if we have one input, several destination, then we have to use the demultiplexer. In communication system, we use the multiplexer to carry multiple data like audio, video and other form of data using a single line for transmission. And to map this audio, video or any signal to the any one of the destination, we have to use the demultiplexer in the communication system. So these are the references. The book by R.P. Jain, Modern Digital Electronics, and John F. Packerley, Digital Design Principles and Practices. The figures and truth tables or logic diagrams are taken from the tutorialpoint.com and electricalacademia.com. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.